Today we'll be talking about human marker augmentation with deep learning using constraints. Our project was supervised by Dr. Antoine Phil.
The goal of our project is to generate a set of augmented markers for musculoskeletal analysis. The current state-of-the-art uses LSTMs for this task. However, they are prone to errors when given complex human motion like jumping, bending, lying. Let's take a look at one of such examples. The blue markers represent the augmented markers. Observe that the blue markers penetrate the floor when the person is jumping. This can be problematic when performing inverse kinematics.
So now the question is, how can we solve this problem? Our idea? Why don't we teach the model our knowledge of physical motion? For this project, we used two facts. First, that the human body consists of rigid bone segments, and second, that the human body has a limited range of motion. In terms of markers, this means that markers on the same segment stay relatively fixed over time, and that angles between certain groups of markers cannot exceed human ranges. Based on our literature review, we decided that imposing these constraints in a soft manner, particularly by adding penalty terms to the base model's mean squared error, is the way to move forward. To this end, we constructed three new loss terms. The OLC term, which preserves distance between certain output markers over time, the OAC terms, which ensures that angles between certain groups of markers stay within human ranges, and the IOC term, which preserves distances between certain input and output marker pairs. After tuning the various scaling hyperparameters and independently investigating the influence of each of our penalty terms when added to the mean squared error loss, we get the following quantitative results. As expected, the loss terms are always greater than MSE due to the non-negative penalty terms that we are adding to it. But what's interesting is that despite tuning, the penalty terms form different proportions of the actual loss. For instance, in the IOC case, the penalty term forms 90% of the loss, whereas in the OLC case, the penalty term just forms 1% of the loss, implying that different constraint violations contribute differently to the final performance of the model.
Let's take a look at a visualization of our results. The light blue markers are generated by the IOC model. Observe that during the first point of contact, unlike the baseline markers, the IOC markers do not penetrate the floor, completely resolving the failure in this case. However, during the second jump, the IOC markers, though to a lesser degree, still penetrate the floor, implying that more work is to be done. Why is this happening? On observing the set of failure cases, we notice that most failures occur when there is high velocity motion in one direction. We suspect that this is due to the fact that LSTMs have memory. When an LSTM encounters a marker in motion, it tracks it, and when the marker comes to a halt, it overshoots its predicted marker. In a way, we can think of the LSTM as modeling inertia. The penalty terms we introduced in our loss function oppose the LSTM's memory by constraining the overshooting in the predicted markers. In the first jump, which was off a raised platform, we had two components of velocity, effectively a lesser magnitude in the overshoot direction. Hence, the penalty term succeeded in resolving the failure case. However, in the second jump, we had a stronger vertical component in the overshooting direction. Here, the constraints weren't enough to completely resolve the issue. In summary, incorporating penalty terms in the loss function does resolve the failure cases to a certain degree. However, more work is needed to perfect the model to overcome LSTM memory implications.